It's AP Calculus Unit 5 Review Solutions. To do problem 1 with these 4 different integrals, we should analyze this diagram of the function and find the areas. I've divided it up into other partitions so that this semicircle I've divided into equal pieces. This triangle here, I divided it right where I have a perpendicular from the base to this point on the triangle, so I can do the area of each of these triangles separately. And I'm going to just write in there all the different areas. You'll notice that the areas down below the x-axis are negative because we want signed areas. For the first problem, 1a, we want the integral from 0 to 7, which is that shaded region. So we just add up all of those areas that I have, -6, -4, and +2, and we get -8. It's a signed area. For part b, it says the integral from 3 to 4. Well, 3 to 4 is from right to left, and we would prefer looking at an interval from left to right. So instead of from 3 to -4, we'd prefer this to be from -4 to 3. And our properties say that when you switch your limits, the upper and lower limits, it will be the opposite or negate the integral. So we do that. We know that the areas that we're looking for are these 3 regions, this pi, this other pi, and this -6. So we have 2 pi minus 6, but don't forget, we're going to find the opposite of it, or we're going to negate it. So we have +6 and -2 pi. The third one, it says from -4 to 0, and then it has a constant times the function. One of our properties says to pull out the constant, and now I'm just going to take the integral. Well, that happens to be the semicircle, which is 2 pi. So we can have 3 times 2 pi, which is 6 pi. The last one says the integral from -4 to 7, and we could do that because it's the whole thing up here. It's just adding up all of this area. So we've got the 2 pi and then -10 and the +2. But the problem had more than just f of x, it had +2. So we have also the integral from -7 to 4 of 2 dx. So we find the antiderivative of that, and we're going to evaluate from -7 to 4 using the fundamental theorem of calculus. So we plug in the 4, evaluate it, and subtract when you plug in the -7. We have that, we simplify it, we get 2 pi plus 14. For this problem here, we're trying to we want to divide the area under the curve of log base 10 of x into 4 partitions. And we're going to use midpoint rectangles. So, it says from 1 to 5. So, since we're going to do this from 1 to 5, I started at 1, and then I made my 4 partitions. You can see here they're all of equal width, each one of them. And I found the midpoint of each of those, and those are the rectangles. Now, it is not necessary that you would have drawn this, but it does help. It gives us a little bit of insight as to what it is we're looking for. The main thing is we know this formula that says the midpoint approximation, if our n, meaning our number of intervals, I should say our number of partitions, is 4, is going to be delta x times the function at midpoint 1 plus the function at midpoint 2 plus the function at midpoint 3 plus the function at midpoint 4. Since it's the number of partitions is 4, we're going to have 4 midpoints. We can see, it was easy with the diagram to see that our midpoints are in 1.5, 2.5, 3.5, 4.5. We evaluate each of those. We have to use our calculator, and then we approximate it. And therefore, the approximate area under the curve between 1 and 5 is 1.771. In problem number 3, we're to evaluate the integral of a sum. Our properties say that the integral of a sum is the sum of the integrals. So we take each one of those and we find its antiderivative, and we go up in power and divide by the exponent, the number. The integral of 1 over t, or t to the -1, is the natural log of the absolute value. Don't forget the absolute value bars. Okay? And one of our favorite functions, because the derivative and the antiderivative are the same thing, e to the t is just e to the t. But do not forget, you have your plus c. And that's, the last little bit was to simplify that number that I had there. You can see what I had 9 divided by 1/3, which is the same thing as 9 times 3, which is 27. Next problem, it says to solve dy dx for this. Well, what does that mean? It means to solve for y. We want to have an equation that says y equals. And then they gave us this initial condition. So, first of all, we have to get this in the proper way to solve for y. We multiply both sides by dx. And then we take the integral of both sides, the indefinite integral of both sides, and the integral of 1 with respect to y is just y. On the other side, this is the integral of a sum, so we would take the integral of each part of that. And I wrote it as power x times the square root of x is x to the 3/2. Taking the integrals of each one of those, and don't forget your plus c. But now we go back up here to what was given. It says y of 1 equals 3. What that means is that when x is 1, when the input is 1, the output will be 3. So what we want to do is use substitution. We're going to, wherever we see an x down here, we're going to put a 1, and this whole expression equals 3, or equals y, so we're going to say equals 3. And then we're going to simplify, subtract, simplify again, and we have what our c is. Our last order of business is to take this c that we found and plug it up here into the integral. And there we have it. Problem number 5. Well, let's analyze this a little bit. First of all, it's saying that because the derivative of g is equal to f of x, we know that if we took the integral of that equation, integral of both sides of that is also true. But the integral of a derivative is the function itself. Because it's saying, what's my antiderivative? And that's what it means. And don't forget that we have in the past seen when the derivative is lowercase f, that the antiderivative is capital F. And in Fundamental Theorem of Calculus 1, we've seen it written this way, that when we have a definite integral from a to b, in this case it's from 2 to 6, that we have the antiderivative at the upper limit minus the antiderivative at the lower limit. Well, remember capital F, this antiderivative, is g. So what we want is g of 6 minus g of 2. That's what this will equal. But we also have this integral from 2 to 6 right up here is 8. So instead of writing this integral, I'm going to write 8. And wherever I see g of 2, that was also given right here. G of 2 is 4, so I substituted that in. Solving for g of 6, we get 12, which is what they were asking for. Problem number 6, 2 different integrals to evaluate. So the first one, we take the antiderivative of sine, and we get negative cosine. We're going to evaluate that from I can't see that, from pi over 6 to pi over 4. And using the Fundamental Theorem of Calculus 1, we plug those into the antiderivative, and we simplify, and we evaluate, and we have it. We take the antiderivative of x cubed plus x, and we're going to evaluate that from 1 to 2. Using Fundamental Theorem of Calculus 1, we plug that in, and evaluate, and we have the answer 21/4. The average value formula that we were given, 1 over the difference of the interval, I mean b minus a, of the integral from a to b of f of x. So in this problem, that's 1 over 4 minus 1. And then we have the integral from 1 to 4. And I wrote that as a power. Instead of 1 over x squared, I wrote x to the negative 2 because we have our power rule. And we have 1/3 times negative x to the negative 1. This negative is really negative 1 times this, so I'm going to take that constant of negative 1 and multiply it times the 1/3 and write it as negative 1/3. Use Fundamental Theorem of Calculus 1 to evaluate. And now we can multiply those. A negative times a negative is a positive, and we get positive 1/4. Number 8. Okay, let's talk about this. Read this. R is some region and under a graph makes an area under a graph. Well, the graph is 1 over the square root of x. Again, you don't have to graph this, but it does give you some context by looking at the graph and realizing this is what the function 1 over the square root of x looks like. Right? And then I did this from interval from 4 to 9, which is what they asked when I shaded that in. So this shaded region, this is what we're trying to find. So I have the integral from 4 to 9 of x to the negative 1/2. Take the antiderivative and evaluate it from 4 to 9, and I get 2. Okay. Now comes the next part, which is a little bit more interesting to think about. It says there's some line k, so I put a line somewhere in there, that divides that area up equally. Now, because this is curving, this line is not necessarily halfway between 4 and 9, because this area goes up higher here and it's lower here, so it's not going to be halfway between. And what we want to know is, where is it exactly? Where is this line so that both of these areas are exactly the same? Well, since they're exactly the same, and we know from part A that the area is 2, that means that each one of those areas happens to be 1. So let's just look at one of those areas, from 4 to k. And we know that that area is going to equal 1. So we're going to find the antiderivative and use the fundamental theorem of calculus 1 to evaluate. And we end up with this 2 root k equals 5, or root k is 5/2. Square both sides, and you get that k is 25/4. Again, you didn't have to graph it, but sometimes drawing a picture helps you to understand what it is you need to do in the problem. Problem number 11. The numbering kind of messed up, but it skips from problem 8 to number 11, but these are all the problems you're doing for your review. And this one again, it says the capital F, meaning the antiderivative of this, but evaluated here. If I take the derivative, well, let's think about this for a second. This notation, f prime of x, is the same thing as if I wrote d dx of f of x. Okay, so well, I should have had a dx after there. I'm sorry. Let me fix that. It should say dx. There we go. And, whoops, that's in the way. Anyway, we have now the derivative of the integral, because that capital F of x is this integral. Well, this happens to be the fundamental theorem of calculus 2. Right? And that told us, with a chain rule, that when you have the derivative of an integral, you just plug in this upper limit, which normally is just an x, into this function, and it will just become that function. But because it is it's not just simple x, it's x cubed, you have to also multiply it times the derivative of that upper limit, and therefore we get the answer of 3x squared times sine of 2x cubed. Last problem is this graphing problem. We're given this derivative, and we want to find the original function, the antiderivative, the graph of it. So there's a couple things we're going to look at. And first of all is at 1, because we don't have any output values here. We do not have any numbers on the vertical axes. We've done problems where we did have these values, and we could actually come up with some of the actual points to graph. We don't seem to have that here, except for this one place here. I know that when x is equal to 1, that this function f of t is 0. We know that to be true. And what I'm really interested in is what's going to happen at g at 1. What is g of 1? Well, over here it's saying when I have g of some x, I use x as my upper limit. So I'm plugging in that 1 as an upper limit. But our properties of integrals say when your lower limit and your upper limit are the same, that integral will have a value of 0. So therefore g of 1 is equal to 0, and that means that 1, 0 is a point on the graph of g of x. So this point right here, which is on the derivative f of t, it is also on the graph of g of x. So I plugged that in. I made it nice and blue there. Now let's look at other things about this derivative, this function, this derivative. When you have a maximum of a derivative, it is a point of inflection on the antiderivative. And when you have a minimum on the derivative, it is a point of inflection on the antiderivative. Wherever the derivative is negative, the antiderivative is decreasing. Wherever the derivative is positive, the antiderivative is increasing. So we've got that knowledge. And here we've got a decreasing, where our derivative is decreasing. We know that the antiderivative will be concave down. When the derivative is increasing all this way from point of inflection to point of inflection, that our function will be concave up. And then it has a point of inflection, and then now the derivative is decreasing, so therefore the antiderivative, the original function, will be concave down. We are now just about ready to graph this. The last little bit is to recognize that when the derivative is at 0, here at 1 and at 5, that will be a maximum or a minimum for our antiderivative. Minimum is because it was increasing and then, actually it was negative and then positive. So we've got a decreasing function changing to an increasing function. So that shows us that's going to be minimum, and then we have our maximum here. So now we're ready to see it. And here it goes. We have a concave down, and it turned to concave up. We have that point. It's still concave up. Point of inflection, concave down, maximum, and then it comes to some place of ending. So we have these critical places here where we had a point of inflection, we have a minimum, we have another point of inflection, and then we have a maximum.